turbo engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
Advances.
questions,
Research.
technology.
Unbelievable.
Without further ado,
This is The Naked Scientists.
Hello and welcome to The Naked Scientist, the show where we bring you the latest breakthroughs in science, technology and medicine. I'm Will Tingle. This week, our attempts to map the dark universe. As the new space telescope Euclid seeks to unlock the mysteries of dark matter and dark energy, we ask why their secrets have eluded us for so long.
From Cambridge University's Institute of Continuing Education, this is The Naked Scientists.
Perhaps the more we know about the universe, the less we understand. Our grasp of the universe, from the macro to the micro, is still very much in its infancy. We have many mysteries to solve about the nature of existence, but if you were to ask a physicist or a cosmologist which mystery they'd want to unravel, there's a very good chance you get a response like this.
For me, it's very clear. What is dark matter? I mean, it's absolutely sure that it's there. There are several different ways of observing its existence, but nobody has got the slightest clue what it is.
That was Lynn Evans, project leader of the Large Hadron Collider, in an interview with us earlier in the year. And I wish that I could say, don't worry Lynn, I'm on the case now. But the short answer to what is dark matter and energy is, we still don't know. But what do we know? There are two entities in the universe which remain inscrutable, almost uncannily mysterious. One is responsible for clumping stuff together, the other responsible for pushing stuff further apart. They are dark matter and dark energy. Together, they make up 96% of the universe, dwarfing the regular matter that makes up stars, planets, and you and I in terms of abundance. But beyond these first few points, information on these two things is pretty non-existent. Their darkness is derived from the fact that we simply cannot observe them. They just don't interact with light or anything else on the electromagnetic field from which so much of our observational data comes from. In fact, aside from gravity, there isn't that much either of them interact with at all. So, why do we think they might exist in the first place? Let's kick off with dark matter. To take us through the timeline of discoveries is Durham University's Francesca Chadha-Day.
The first hints at dark matter were really discovered by Zwicky in the 1930s. And he was looking at galaxy clusters. So these are massive structures. And at that time, when Zwicky was working, most physicists assumed that the matter we can actually detect directly with our telescopes was all there was. And Zwicky observed the Coma galaxy cluster, and he found that the matter he could see, the luminous matter, was moving much faster than expected. And for matter to be moving that fast without flying off into space, there needs to be a certain amount of mass pulling it in with its gravitational attraction. So he estimated the total mass of the cluster, and he found that that estimated mass was much bigger than could be accounted for by the luminous matter alone, the matter he could see. So this was really the first hint that there was some additional matter in that galaxy cluster, which Zwicky termed dark matter.
How was then that theory taken a step further?
So the next big piece of evidence came from another astronomer, Vera Rubin, and she was looking not at galaxy clusters, but at galaxies. She saw exactly the same thing. She made detailed measurements of how the velocities of the stars changed with their distance from the center of the galaxy. And again, she found that the stars' velocities were much too high to be bound to the galaxy by the mass of the luminous matter alone in that galaxy. So again, to make those velocities of stars make sense and to make them not just fly off into space, there needed to be a large additional component of mass in the galaxy, which she concluded would be provided by this dark matter.
Francesca Chadha-Day, and we'll be hearing more from Francesca about dark energy a bit later on. As Francesca outlined, dark matter could well be what's preventing galaxies from spinning themselves loose by nature of just being there and adding some mass to the carousel. But what is the nature of the matter itself? Well, just over 10 years ago, we put in a call to the University of Edinburgh's Catherine Haymans. She talked us through what the understanding of dark matter was at the time. So, after a decade, are we any closer to answering the question, what is dark matter?
Okay, so there are various different contenders for the dark matter particle. The top contender for a dark matter particle is something called a WIMP, which stands for Weakly Interacting Matter Particles, because astronomers just love their acronyms. So the WIMP particle is something that interacts through the weak force. And the top contenders for WIMPs was supersymmetric particles. So your listeners might be familiar with this idea of string theory, this sort of underlying theory that can explain our universe. And this proposes that there will be additional particles that are sort of mirror images of the particles that we know and love, the quarks, the bosons, the leptons. So there's that group of particles that could be dark matter. There's also something called axions. Axions are actually super interesting because they come in all different ranges of energy and masses. It's a theoretical prediction, but in principle, the sort of landscape of different axions that you could have could, in principle, explain both dark matter and dark energy. So lots of excitement about axions as well.
Well, now it is time to put you on the spot. It's time for our 10-year retrospective on dark matter. 10 years ago on this programme, and you said that we know that it is weakly interacting, we know that it is cold, and we know that nobody has detected the particle yet. Are we still 3 for 3 in that regard?
Okay, so I would say we are definitely sure it's still cold. So dark matter dictates when and where the galaxies form in our universe. And if you look at how galaxies are distributed across the universe, that only makes sense if there is dark matter around to sort of seed that galaxy formation. And you can look at the distribution of the galaxies, and that can tell you about the properties of the dark matter. And it has to be cold, which means sort of slow moving. If it was much warmer, then it would have a lot more momentum in the early universe, which would change the way we see the distribution of galaxies today. So I'm still happy with the cold. Now, the weakly interacting, that's still the best contender for dark matter. But what's changed over the last 10 years is that we haven't had a big discovery at the Large Hadron Collider. So the Large Hadron Collider at CERN was built to find the Higgs boson. Success, Nobel Prize, well done everyone. But it wasn't supposed to just find the Higgs boson. That was supposed to be the tip of the iceberg. So your models of string theory that predict these supersymmetric particles, the lightest supersymmetric particle in this theory should have been detected by the Large Hadron Collider by now. That was supposed to be the next thing found. And the fact that it hasn't been found has thrown into question this whole string theory and supersymmetric landscape. Now, it could be that they're just much lower mass than can be detected, lower energy that can be detected by CERN. And maybe when it has its upgrade, these particles will pop out. But I think because the simplest theory hasn't been borne out in experiments over the last decade, people have been getting more interested in this axion alternative.
And have we been able to detect the particle yet?
Nothing yet, but the error bars are going down. So you can either create one of these particles or you can catch one of these particles. And the fact that we haven't managed to create or catch a particle yet means you're reducing the limits on how massive or how energetic it can be. And so we're sort of narrowing down the space, but no, not detected yet.
When compared to other dark entities that we will talk about a little bit later on in the show, it feels like we have an idea of where it is, what it's doing, and what it could be. It feels like there's a tangible, genuine chance that we might be able to crack it. Do you think we may uncover its secrets, say, within our lifetime?
If it's a dark matter particle, then yes, I think we will, just because the techniques and instrumentation are growing so fast now. We've got the upgrade coming at CERN, and also the direct detection community are clubbing together to essentially put all of the liquid xenon in the world in one place. So a really massive butterfly net to catch these tiny dark matter particles. And excitingly, Will, I don't know if you've heard about this, that there are plans to install this at Bolby Mine in Yorkshire. Can you imagine the headlines, dark matter detected in Yorkshire? I love the idea. And so there is work on the way to develop this mine as a future dark matter detection site, which would be fantastic. So I am hopeful. If the answer to dark matter is that it is a particle, then I would hope that we would detect it in my academic career. But it could be that it's something else entirely. I mean, it's such an open question at the moment, I think. And there's lots of work in different areas to try and explain this phenomenon, because the simplest answers haven't panned out yet.
Catherine Heymans. As Catherine says, the Large Hadron Collider is currently unavailable to shed any further light on the nature of dark matter, so we must look in a different direction for the moment. Enter the Euclid mission. Euclid is a space telescope developed by the European Space Agency and the Euclid Consortium. It was launched in July of last year with the objective of looking 10 billion years into the past to track how the expansion and formation of galaxies might have been influenced by our two mysterious friends. I've been speaking to the European Space Agency's Director of Science, Carole Mundell.
The Euclid mission is an iconic and unique world-leading space mission and combines some unique capabilities. What it's particularly good at is very wide field imaging. We also have spectroscopy in the optical and the infrared. But combining that wide field, patches on the sky, with very sensitive detectors, so we can look back in cosmic history very far and see very, very faint features in the universe, but also with a very third and very important feature, which is very crystal clear vision, so diffraction limited optics. And the reason that we need to have the wide field, the sensitivity and the precision is because we are going to map in the next 6 years the entire extragalactic sky back to 10 billion years in cosmic time. And what we will deliver to our cosmologists in the Euclid Consortium is this beautiful, precise data that they will go in and they will look for tiny little distortions in the shapes of billions of galaxies. And they will use those distortions to look for the distorting signatures of dark matter and how that dark matter couples to dark energy through cosmic history. And so it really is a huge step forward in our technical capability to study the laws of physics beyond where we currently understand them.
The one thing that I've really grasped when talking about dark matter and energy is that we can't see it. Why have you chosen to use a telescope?
Yeah, so this is a great question. And whenever we show the beautiful early release images that we've taken with Euclid to test our engineering, people always say, show me where the dark matter is. And what dark matter does is it changes the way space-time bends, if you like. And so we can look at big groups of galaxies where we know there's an awful lot of matter there. And when the light from background galaxies comes through that so-called gravitational lens, we actually see slight distortions. When you're very close to the center of a big concentration of dark matter, you see big distortions. So galaxies might be twisted out into thin arcs. And when you go further away from that concentration, although there is still dark matter there, you will see tiny little distortions in the galaxies. And it's being able to do that over big areas of the sky to control on the systematics so that we can then map out that distribution of dark matter through cosmic filaments that we think are where the galaxy clusters form at the intersections of these filaments, and really map that back, that 3D mapping through cosmic time over big areas of the sky.
The fourth mention of time, is this something new that Euclid is bringing to the research into dark energy and dark matter? By seeing how these things behave over time, we might get more clues as to what they are.
Yes, absolutely. And that's why we have the spectroscopy on board as well. Just taking photographs isn't enough, because obviously that third spatial dimension is also a time dimension. So as we go further out in cosmic distance, we go further back in time. And so by adding on the so-called redshifts, so where the galaxies are in space, but also measuring how the universe expands, putting all of that together across these vast areas is what really gives us that three-dimensional time machine.
We're very early on in this expedition. Have there been any standouts so far?
There have, actually. I mean, we began the survey in earnest in February of this year. We're already 4% of the way. We took 1 day of data back in the summer once we got through commissioning and we made sure that all of our instruments and our spacecraft was working well. And we've really given those images to scientists to start to mine them. And I think in terms of the dark energy, dark matter question, we're really showing that the precise measurements that the cosmologists want to make will be feasible. How you can see in small dwarf galaxies, small star-forming nurseries, on the other end of the spectrum, globular clusters, so ancient balls of stars, probably the oldest structures in the universe, And we've been able to detect the lowest mass stars out to the edge of the globular cluster, but also resolve all the detail in the middle. So you can actually do the physics of dark matter within the globular clusters. And also we've got the exquisite sensitivity to detect what's called the intra-cluster light. So these are individual stars that have been torn out of the galaxies in the galaxy cluster by the force of gravity. And they're also a tracer or a proxy for the gravitational potential in the hidden dark matter. So it's a treasure trove. And I think the scientific community is just starting to wake up to how they're going to have to transform the way they mine these data, the way they ask questions of astrophysical and astronomical data, because it's really too much detail and too much richness to be able just to gaze at the images. We all gazed at the images to start with, and then you start to think, wow, what's the physics you can do here? So I think it will transform cosmology, but it will also transform modern astrophysics.
Strong words from Carol Mundell. We look forward to seeing what else Euclid sends back.
The Naked Scientists podcast is produced in association with Spitfire, cost-effective voice, internet and IP engineering services for UK businesses. Find out how Spitfire can empower your company at spitfire.co.uk.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
You're listening to The Naked Scientists with me, Will Tingle. Still to come, could there have been a third mysterious force that affected our universe's formation? But before that, I hope you feel like you grasped at least some concept of what dark matter might be, because now we must turn to something even more abundant, yet even less understood: dark energy. So, how did Adam Rice, Saul Perlmutter, Brian Schmidt and their teams even conceive of its existence? Francesca Chaladay is back with the timeline.
So the team in 1998 were looking at the expansion of the universe, and they were observing actually a special kind of supernova called a type 1a supernova. And this occurs when a white dwarf star eats another star. But the special thing about this kind of supernova is it's what we call a standard candle, which means it's always the same brightness. And we know what that brightness is. So because of that, we can use these supernova to work out how far away the star is. And we can also use an effect called redshift to work out how fast those stars are moving away from us. This happens when the source of light is moving away from us. The wavelength actually changes. It becomes longer, which means in invisible light, it becomes redder. And it really allows us to track the expansion of the universe throughout its history. That team got a bit of a surprise because what they found was that the expansion of the universe is actually accelerating, it's speeding up. And it's very puzzling because to explain this accelerated expansion, we need some kind of energy source or effect in our theory. And that's what we call dark energy. And you may notice that this explanation is a bit vaguer than the explanation for dark matter. And that's because the question of what dark energy is vaguer. With dark matter, we're looking for a kind of particle that we don't know about yet that doesn't interact with light very much. With dark energy, we don't really know what we're looking for. It's really just the question of why is the expansion of the universe accelerating? And dark energy, to my mind, is just the answer to that question.
Some of the most compelling arguments I've seen for universal expansion come from the idea of the cosmological constant and vacuum energy, that there's this ubiquitous energy density that exists throughout the universe and causes its expansion. Is this what a lot of theoretical physicists are running with at the moment?
I think most physicists think there is something more fundamental going on. The current theory is really just kind of, oh, there's this number and you put it there, and would like something more fundamental than that.
Francesca Chaladay. We know that about 5 billion years ago, something caused our universe to start expanding at an accelerated rate, and if that is the case, this thing must make up about 70% of our universe. But that's it. Everything else beyond this point is purely hypothetical. We might not have the mathematics yet invented to pass this kind of information. So with that being said, I took a trip down to the University of Cambridge to see theoretical physicist Anne-Christine Davis to talk us through what dark energy could be.
It's difficult to define dark energy. What we know is that there's something mysterious that makes up about 70% of the energy density of the universe and is currently causing the universe to undergo a period of accelerated expansion today. What it is still an open question. There are lots of ideas around. It could be that Einstein equations are wrong and we need an addition. It could be another particle causing this expansion. We actually really don't know. It could be something like the chameleon theory, whereby you have an extra field, an extra particle, scalar particle, and its behaviour is such that its behaviour changes in the environment. So it can have more massive in the solar system, and the range of its force is rather short. So it doesn't affect gravity in the solar system, but it could affect the behaviour cosmologically where the density is much lower. It's something that we can work with, but we can't quite make it satisfy everything we want to do with dark energy. It's a bit disturbing. I find it rather disturbing that things we don't know we dub dark.
If, though, as you say, or we theorise the existence of this dark energy because the expansion of the universe started speeding up, was it always there?
Probably. It was probably always there in the background, but it only came to dominate later on in the development of the universe. You can imagine the stages in the history of the universe as a bit like a marathon race. Let's say a sprinter, 100-metre person, a longer distance, 400, then a middle distance runner, and a marathon runner, and they all have to run a marathon. When they start out, the sprinter will stream on ahead. That's the first period of inflationary expansion that we think the universe underwent. Then we get another period when the runner used to, say, doing 400, 800 metres will take over. She'll continue for a bit, and this would be like the period where the universe was dominated by radiation. But she'll tire after a while, and then the middle distance runner will take over and will dominate the race for a long time. And this is the period when the universe is dominated by matter, by ordinary matter that we know and love. And we can feel the effect of this. We see the galaxies forming, the stars. At the very end of the race, the marathon runner will overtake. And that's the late period of accelerated expansion or dark energy that we're undergoing now. And that's a bit like dark energy. It was there, it's only dominating today because everything else decreases faster than dark energy does.
Is there a reason that we know of that we can't detect it? Because we're getting pretty good at finding stuff out in the universe, but if 70% of it is an energy that we can't detect, that seems quite extraordinary.
I think it's quite embarrassing, actually.
When we have all of this visible, regular, normal energy, I suppose, as we dub it, if it's making up 70% of the universe, is dark energy in and among us right here, right now?
Presumably. It depends precisely what it is. So, for example, if it's due to a chameleon-type particle whose behaviour depends on the environment, it would barely interact in the solar system, in this room, that we wouldn't detect it. But yes, if it should be there, there's no reason why it shouldn't be there. It could just be something like a vacuum energy that we don't know about.
Now, this is pure blue sky thinking here, but could the answer be in something, say, a dimension higher than we can perceive, and it's not something we will ever be able to know?
Oh, it could be. I mean, there was this film, Interstellar, where they went into the extra dimension, and it was using theories that were around at the time. One of the advisors was Nobel Prize winner Kip Thorne. It could be something like the influence of the extra dimension that is there, but we can't see it, but we feel the effects of it. It could well be. I don't know how we would work that one out, but that could be that we have 5 dimensions, or some theories 11 dimensions. One of them is sticking out and giving us rise to this mysterious dark energy. I think there's a difference between dark energy and dark matter, a big difference, in that we really do sort of feel dark matter in the way that galaxies behave, and dark energy is something much more mysterious than that.
And Christine Davis. So this is currently the most unknown yet most abundant entity in our universe. Our attempts to even hypothesize what it is are still in their infancy, so what are we doing to learn anything we can about dark energy's nature? We heard a bit earlier from Carol about the information that Euclid is sending back about the history of our universe. But how does that cosmological data further our understanding of dark energy? I've been speaking to Lawrence Berkeley National Laboratory's David Schlegel.
The data about dark energy is only starting to get good now. The only observable that we have right now for dark energy is how it's been pushing on the universe today compared to the early universe.
If that is the only current observable that we have, where do you even go from there? Is there a part of the cosmos you can look at to provide any more kind of insight?
Yeah, no, that's a good question. And for studying dark energy today, because we only have this one observable that doesn't fit, which is the history of the expansion of the universe, it means you can't look at just one part of the universe to make a measurement of dark energy. So I'm in the business of making these giant maps of the universe, these giant three-dimensional maps. If you only make a map of the local universe, and I should say for the cosmologist, the local universe is the billion light years nearby. If you did that, that map tells us very little about dark energy. So the data that we have right now, discovery was 25 years ago, but we're still in the early stages of understanding dark energy. So in the intervening years, we've made the measurements that confirm very strongly that dark energy exists and approximately what its influence is on the current day universe. But we don't have very precise data on what's happened between the early universe and today. And so the data right now, it really is, it's confirming the discovery, but not much else. Euclid and this next generation of experiments, what we're doing is making precision measurements of what the effects of dark energy have been as a function of time. And so one of the ways that we phrase this is, has its effects been evolving with time? And so that would be what we would call a dynamic dark energy, where it wasn't the same in the early universe as it is today. We know fractionally in the early universe it was less important, and that's because the universe was more dense. It hadn't expanded as much. So shortly after the Big Bang, the universe is expanding. You have the forces of gravity attracting matter to other matter, galaxies to other galaxies. That's slowing down the expansion. Dark energy was still there, but proportionally, it was only a small fraction of the energy density of the universe. Then fast forward to today. Today, the universe has expanded enough that dark energy, even though it's approximately constant volume of universe, proportionally, it's a much more important effect on the universe.
So by mapping this out and understanding whether or not it's dynamic, would you be able to sort of cross off a few contenders as to what it might be, or might be slightly composed of?
Yeah, no. So the future, I mean, especially if you look at the far future of the universe, we really have no idea what's going to happen. So it appears that the effects of dark energy, it's very close to a critical amount where the universe, maybe it expands forever, maybe it even undergoes a big rip where the whole universe essentially rips itself apart, or maybe dark energy evolves such that it turns off or freezes out. And in fact, there's a glimmer of data just from this year, 2024, that suggests that that might be the universe that we live in, where dark energy may actually be evolving so that it's becoming less important with time, but we don't know yet.
It seems extraordinary, and the part that really bakes my brain is the nature of dark energy suddenly accelerating the universe about 4 billion years ago. And as you're saying, it might be able to evolve further in the future. It almost sounds like something that has its own mind to make up.
I keep saying this, but we just know so little about it. And when I introduced myself, I could have introduced myself as an expert in dark energy, which unfortunately doesn't mean that much. Like it's not hard to become an expert in dark energy because we know so little about it.
Do you have a favorite idea as to what it might be?
That's a very good question. So what we've been talking about are the current knowns and unknowns in the universe, where the two big unknowns are the nature of dark matter and the nature of dark energy. There is another unknown that we have not mentioned, which is what happened in the first moments of the universe after the Big Bang, where what appears to be the case is that there was an inflationary force that might have been another force, very much like dark energy, that accelerated the expansion of the universe for some period of time, although in that case, not for billions of years, but just for a tiny fraction of a second. And that homogenized the universe that we see today. And then that force, or whatever it was that we call inflation, turned off. So that's an example of what we would call an inflationary force, if in fact that's how it behaved. So that is yet another force that we think we can design experiments to study actually in the future. But the intriguing thing to me is we know of this other force that we think was dynamic, inflation. There's this force that we see today, dark energy, where we know very little about it. And I guess intriguing to me would be, are these two unknowns or are these one unknown? So in other words, are we talking about the same force? We just see them at different times and we're labeling them differently.
David Schlegel. So, the hunt continues to uncover the secrets of the dark universe. But the technology and wherewithal to even begin looking at these entities in a meaningful way has only just kicked into gear. The next few years could provide more answers than the last 90 years combined. And whether the answers come from the intergalactic cosmos or a mine in Yorkshire, the universe might not stay dark for too much longer. That's it for this week. Join us next week when we're looking at the subject of gambling addiction. What exactly is it, and what should you do if you're worried that it's become problematic? The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce, I'm Will Tingle, and from everyone here at The Naked Scientist, thank you for listening, and until next time, goodbye.